All right, so this video is a review for the final exam for chapters 1 and 2. So the first thing we want to do is remember that we use the addition property and the multiplication property to solve linear equations, such as this one right here. So the first thing we're going to do here is combine some like terms here. Notice what we did. We combined the -9 and the -1 to get -10, and then we combined the 4x and the 8x to get 12x. So we'll continue on. Looks like they're going to subtract the 17x from both sides. And that leaves us with -5x equals -10. So the last thing to do would be to divide both sides by -5. And we would end up with x equals 2. Once again, negative divided by negative ends up with a positive. So what we did was we used the addition property and the multiplication property to solve this equation. Now, remember the way that you can always check it by plugging in the result, the answer that you get, the solution that you get for each x into the original equation, which is what we do here. And it does check. So, and then remember the final thing is we put the solution that we found into a solution set, and that solution set is indicated by brackets around the solution set. All right, so the next thing we want to talk about here is interval notation. So what we have here is an inequality, and we want to write the inequality in interval notation, and then we'll also graph the interval of this inequality. So what we have here is x greater than or equal to -3. So the first thing, when we write this in interval notation, remember we put, since it's a greater than or equal to, we use a bracket around the -3. And then since this is greater than or equal to, it goes to the right, which is towards positive infinity. So we can write this on the interval, on the number line here. We would put a bracket at -3, and we would go to the right to positive infinity. So sometimes it's easier to write the number line version and then write the interval notation, but however you can get it done. But remember, because this is greater than or equal to, we use a bracket, and if it was just simply greater than, we would use a parenthesis. But those are some things that come from that chapter. So now let's look at this one. Here we have 0 less than x less than 3.5. Now notice we use parentheses here. The reason why we use parentheses is because we have a less than sign, not a less than or equal to sign. And then this just happens to be a closed interval here because it's 0 to 3.5. But it does emphasize the use of the parentheses. So if we were to write this on the number line, we would put a parenthesis at 3.5, a parenthesis at 0, and then we would fill in the middle there. So when we're using the addition property to solve an inequality, we do it pretty much just like an equation by combining like terms, isolating the x variable, and all those things that we normally do. So here we have our inequality. First thing we're going to do is subtract 4x from both sides. And then we will subtract 3 from both sides. And we end up with our inequality here. So we got x greater than or equal to -4, but we make our money here is whenever we turn this into interval notation because sometimes we're not so used to using interval notation. But we're looking at greater than or equal to -4. So here's what so since it's greater than or equal to, we use a bracket around the -4, and since it's greater than or equal to, we go to the right, which is infinity. So to put this on the number line, we would put a bracket at -4, and we'd fill in to the right of -4. Now there's one thing that we do need to keep in mind when we're solving inequalities, and that is if we ever divide or multiply by a negative number, we rotate the sign. So in this case, we would use the multiplication property of an inequality by dividing both sides by -9. Notice that they have rotated the inequality sign here, and they've indicated it in red to emphasize that we've rotated the inequality sign. So just remember, if you do divide or multiply by a negative, you got to rotate that sign. Now we're looking at x greater than 9. So since it's a greater than, we use a parenthesis over the 9. And since it's greater than, it goes to the right. So it's 9 comma infinity. And we'd put a parenthesis at 9. And we would fill in to the right of 9. All right, so this is the one question that you don't want to miss on the final exam. It's very easy, but students often miss it because maybe they perhaps overlook the simplicity of it. So in this case, you're given the slope and you're given the y-intercept, and they want you to write the equation of the line. So what we do here is basically we're going to use, so the y equals mx plus b, and we determine that the slope is m equals 2, and based upon this, the y-intercept here, b, is -3. So we simply plug in the slope for m and this y-intercept here for b. So we just simply move this into y equals 2x minus 3. You don't want to miss this question on there. Just plug in m and b here. Now, one question is going to ask you to find the slope. The slope is not hard to do. It's just sometimes we get the numbers mixed up. So one way to do it would be to label your sets of points. As here you have x1 and y1, and then here you have x2 and y2 in red, blue for y1, x1, red for x2, y2. Then you plug it into your slope formula. And so we would take y2 here, which is -5. Y1 is 9. And then x2 is 3. And x1 is -6. A couple things to keep in mind here when you do this. Notice that the -5 is the y-coordinate. Y is on top. That's the first thing to remember. Y's are always on top when you apply the slope formula. And we got -5 is over its x component. Notice that -5 is over 3. And 9 is over -6. So the corresponding elements of the coordinates will be on top of one another. And another thing to notice is when we're plugging in this -6, we use parentheses around that. The reason why we use parentheses around that is to emphasize that that's going to become a positive 6. So we end up with 3 plus 6 is 9 in the denominator, and -5 minus 9 is -14. So our slope is -14 ninths. And then this just has a note that we could interchange these. Notice in this case we could make this x2, y2, and this x1, y1. As long as we keep them lined up in the correct way and making sure that your y component is over your x component, as we have here, then everything should work out fine. So, in this situation that we're talking about here, we're asked to write an equation given a slope and a point. So we're given the slope of 2/5 and it travels through the point 3, -4. So we're going to use the point slope form of a line here, equation of a line, y minus y1 equals m times x minus x1. So we plug in the point, we put in the -4 for the y1, and notice we put in the 3 for the x1. And notice that we put in our slope here for the m. All right. Now just clean this up a little bit. This 4 becomes positive. -4 becomes positive. Then we've got everything on the right side remains the same. Now, if you remember, there was something special that we did to this, kind of the big step of this. And one thing we like to do is cancel out this fractional component. You could distribute this 2/5 here and then move everything over, but then you're going to have to deal with finding a common denominator and handling fractions. But one way to quickly do it without having to do all that is to multiply by the denominator of the slope. And this is just one alternate way. It's really handy, especially when you're going in the standard form. So what we do is we multiply everything by 5, which is the denominator of the slope. So we multiply 5 times both sides of the equation. That's 5 times y plus 4. And then notice that the 5 in the denominator of the 2/5 cancels out. So we're left with 2 times x minus 3 because the 5 in the denominator has canceled out. So we go ahead and distribute the 5, distribute the 2, distribute the 5, distribute the 2. Then we subtract the 20 from both sides. And then we solve for y. We divide by the 5 on both sides. And then there we have the final equation written in slope-intercept form. But let's look at a problem more like what will be on the test. It's using the same strategies here to do it. So this is how the problem will be written. So you're going to be given 2 points here. And we're asked to find the equation in standard form. So the first thing we got to do, it says standard form. The first thing we got to do is find the slope. So we go 6 minus 4 over -5 minus 1. 6 minus 4 is 2. -5 minus 1 is -6. That reduces down to -1/3. Very important that you reduce this because you'll end up with a little bit harder numbers to handle if you don't reduce this. So we found the slope. Next thing we're going to do is use the point slope equation. Y minus y1 equals m times x minus x1. We plug in, we choose one of the points. It's always handy to use the one that has the 2 positive coordinates in it. That way you don't have to worry about changing the sign once you plug it into the point slope equation. So we got y minus 4. We took the 4, we plugged it in there. We took the slope, which is -1/3. We plugged it in there for m we got x minus x1. x1 is the 1 here. So there we are. We've got it plugged in. Now the next step is, remember, we multiply by the denominator of the slope because we want to cancel out the denominator. We want to get this all into integers. So we multiply the entire thing by the denominator of the slope, which is 3. So here we are. So we got 3 times 4 minus 1, well, y minus 4. 3 times y minus 4 equals, and then we hold on to this negative 1 here. Hold on to the negative 1 because the 3 canceled out, right? But the negative didn't. So we distribute these. So we distribute the 3, distribute the negative 1. Then we add the x over, add the 12 over, and now we've got everything into the standard form position. So it's x plus 3y equals 13. All right. Now, the other question that you'll come across is you'll be given a set of points, and you're asked to determine whether they're parallel, perpendicular, or neither. This one just says, are they parallel? So here we have one line that passes through negative 1, 2, and 3, 5, and another line that passes through 4, 7, and 8, 10. It wants to know if they're parallel. So the way that we do this is we determine the slope of each line. So the first one we do here, negative 1, 2, and 3, 5, using the slope formula. Once again, 5 minus 2, 3 minus negative 1. Notice the parentheses around the negative. So these problems are not that hard. It's just oftentimes when we plug in the numbers into the slope formula, as I've said before, we often get them mixed up. Notice that the y's are on top. Notice that the 5 is over its x counterpart. The y coordinate is over its x counterpart. 5 is over 3. 2 is over negative 1. So 5 minus 2 is 3. 3 minus negative 1, same thing as 3 plus 4, we get 3/4. Then we find the slope of the other line. Again, using the slope formula. 10 minus 7 over 8 minus 4. The 10 is over the 8. 7 is over the 4. We get 3/4. So notice these two slopes are equal. Since the slopes are equal, the two lines are parallel. That makes logical sense, that if two lines were parallel, then they would have the same slopes. Now, slopes of perpendicular line. Now, their slopes of perpendicular lines are negative reciprocals. So that's basically what we want to take away from this, is that slopes that are perpendicular are negative reciprocals. Unless one is vertical, a line that's going to be perpendicular to a vertical line is a horizontal line. So a line with a zero slope is perpendicular to a line with an undefined slope. Remember, perpendicular means that they intersect at a 90-degree angle. So just reiterating here, so if we had a first slope of negative a half and we had a second slope of 2, for example, notice that these are negative reciprocal. Remember, a negative reciprocal means flip it and negate it. Remember that? Flip it and negate it. If you can flip the slope and negate the slope, then they're perpendicular. So this is an example of lines that are perpendicular. Now, if we had a first slope of negative a half and a second slope of a half, now this is just kind of tempting to say that they're perpendicular. Remember that they are negated, but they're not flipped. So this is a situation where you would say neither perpendicular or parallel. Then we have a final case here where we have slopes that are equal, Remember, when slopes are equal, they're parallel. All right, so now we're going to get into functions. Remember, when we're given a set of ordered pairs, we've got to determine whether or not it's a function. So the first sign here is to look at the x coordinates. Notice that we have a repeating x here. -1 occurs twice. And notice that if we look at this closely, -1 is associated with 2 as well as 3. So this is not a function. The same x value is paired with a different y value, right? So in bold here, in a function, no two ordered pairs can have the same first component and different second components. So looking at B here, notice there is no repeating x's. So in this case, each different x value is paired with a y value. And this does not violate the definition of a function. So in this case, we're given a function f of x, -x squared plus 3x plus 3. We're supposed to find f of -3. Remember, all it's going to do is say find f of -3. And what that's asking you to do is plug in -3 for x. Notice we have in this next piece here, the x is blue, indicating that we're putting in -3 for the x. Be careful when you do this, because remember, because of PEMDAS, we do the exponent first because of this negative sign. Remember, I said that negative sign is what typically gets people on these things. So notice we're going to square -3 first, then we apply the negative. So that becomes -9. -3 squared is 9, and then we apply the negative, -9. 3 times -3 is -9 plus 3. So we got -18 plus 3, -15. So a couple things to remember here. The first one is that when it says f with in parentheses -3, what it's asking you to do is to plug in the -3 for the x. The second thing to keep in mind here is, remember, this negative on the outside means you do the exponent first. You square the value first, then you apply the negative. So those are a couple things that usually go wrong with that particular question. All right, so we're going to find domains and ranges from graphs. So we're given this graph here. As you can see in blue here, we have a parabola that's kind of laying on its side there. A couple things to notice about this graph. Remember, this is assumed to go on forever. This is assumed to go on forever in this direction. So the first thing it says is decide whether the graph is a function. So is the graph a function? We administer the vertical line test here. And notice that it intersects the vertical line intersects the graph more than once. So that means it is not a function. It fails the vertical line test. Then it wants us to give the domain and the range. So remember, the domain, as it says down here, the domain is all values of the independent variable x. That's the domain. So the domain is, remember, this goes on forever to the left, right? So negative infinity up to this point here, right here, on the tip of this graph. So 1, 2, 3. So it goes up to 3, and it includes 3. So we put a bracket around 3. That's the domain. Then it asks for the range. Remember, the range is a set of all values of the dependent variable y. So that's all these going in the vertical direction. And remember, this thing goes on forever. So that means that our range is going to be negative infinity to infinity, because this thing goes on forever in both directions. Now, this one is the one that gets a little trickier, more tricky. So first off, we're going to determine whether the relation defines y as a function of x. Anytime it says y equals, and then there's an argument in x, we're going to say that that is defining y as a function of x. Then it wants us to give the domain. So y can always be found by multiplying -2 and adding 7. So each value of x corresponds to just one value of y. This is a linear equation, and it doesn't have any excluded values or anything like that. So that means that the domain is going to be negative infinity to infinity. The equation, a line is always going to have negative infinity to infinity as its domain. But something tricky happens here whenever when we have a square root function. If you remember correctly, when we take the square root of a negative number, that results in an imaginary number. Remember that from chapter 7. So what we want to do here, we're going to we don't consider that when we're dealing with functions. We don't consider that to be a reasonable domain to take the square roots of negative numbers. So what we're going to do here is, when we have a square root function, is exclude any values that make the radicand. Remember, the radicand is the what is underneath the radical. That is the radicand. So we're going to find any values that would make the radicand negative. So in other words, we're going to include values that are greater than or equal to 0. That's excluding any negative values of this. So we set up an inequality here. We're setting the radicand greater than or equal to 0, and then we solve that. So we'd add 6 to both sides, then we would divide by 5 on both sides. So now we're getting to the domain of this square root function here. Now we've got to turn it into interval notation here. So in the way that we do that, since it's a greater than or equal to, we're going to put a bracket over 6/5. And since it's greater than or equal to, we go to the right, and to the right is positive infinity. So just remember, anytime you have a square root function and we're trying to find the domain of it, what we do is set the radicand greater than or equal to 0, and then solve that inequality, and then we will get the domain of that square root function. And by the way, this is a function because it's y equals, and it has some kind of argument of x.